Okay, so let's go back to R and work on these kinds of ideas there. If I have this population, if you have a population data frame in R, you can take a random sample from it um, by using the slice sample function. So here I'm taking a random sample of 1,000 people. I set n equals 1,000. If I do slice sample n equals, so here the first n, this is the argument. I'm saying that pass the number n that I have here into the n slot of the slice sample function. If that doesn't make sense to you, review the way that functions and arguments work in R. So I can now do this repeatedly. So in the real world, you're just going to have usually your one sample. But we have to imagine what would have happened if we were repeating this experiment many, many times. Why is your one sample special? It's not. You have to consider what other samples you might have gotten in order to be able to say anything about probability or the chance that what you got is a representative result. So we have to at least be able to imagine that. And if we're imagining it, we might as well simulate it in the computer, where we can tangibly see things, what's going on, without having to do math and think about theory. So I'm just kind of showing you how to do that. If you have a population data set that's simulated, you can take repeated samples like this. So sample 1, sample 2. This will be a different random sample. And now I can calculate certain statistics, just counts in the samples. So here I'm counting how many diabetics are there in this first sample. Here I'm counting how many diabetics were there in the second sample. Those are going to be different numbers, right? So in this example, I got 88 and 106. And I think, remember, the rate in the whole population is actually, it should be 100. We have like one out of 10 people is diabetics. So on average, we should get about 100. So here I just took 2 samples, but ideally we would want to know what would happen if I did this a lot of times. And we can do that in R. We can just kind of copy paste our code and wrap that up into what's called a loop. So that's what I've done here. So this code here, where I'm taking population, taking a random sample, counting the number of diabetics, I'm going to wrap that up into a loop so I can repeat it 1,000 times, 100 times, 1,000,000 times. So that's what this code does here. So this is the thing that I'm repeating. And I'm putting that into this little bit of code here. Sorry, map underscore df. So map, this stuff you can read about in the R for a data science book. I think chapter like 25 or 26. It's not like totally mission critical, at least not yet. Hopefully by the end of the course you'll have seen it enough that you can do it. But if you want, you can just think of this as like a magic spell that says, do this thing on the inside this number of times. So here I'm saying make a vector of numbers going from 1 to 10,000. And for each of those repetitions, I'm going to do this exact thing. And now I'm saving all the results into this data frame called sample counts. So when you do that, the result looks like this. So this is in my first experiment, how many diabetics did I get? In my second experiment, how many did I get? In my third one, and so on and so forth. And I've done this 10,000 times. So you should run that code. And now we can calculate these probabilities that we were talking about abstractly, conceptually. You can actually calculate those empirically. Because you did 10,000 surveys. Now that's not all the possible surveys you could do, but it's a really big number of them. So let's see what the probability is that a survey results we find 10 diabetics, more than 10 diabetics, 13, 20. And let's do this. So you can make a histogram of those survey results and think about how you might use that to argue against the researcher who we previously discovered who was claiming that the rate of diabetes has actually gone up substantially in New Zealand because they got 13 diabetics in their sample. Okay, so let's copy this code here, and we want to run surveys with 100 people each, and we want to do that, let's just be explicit here, 10,000 times. Okay, let's give that a shot. If it takes a minute, no worries. Okay, so let's have a look. All right. So that's these numbers seem reasonable. So let's calculate the probabilities now that we want. So remember, the probability is just the proportion of times that something happens in a population. So what we have here is a population of 10,000 surveys. So all we need to do to calculate certain probabilities is count how many times that thing happened. So if we have here our sample counts data frame, we can just ask, for example, the probability of the survey finding more than 10 diabetics. Just filter to the called diabetics. So, filter to the rows where we got a result with more than 10 diabetics. Okay, so we that happened about 4,200 times out of the 10,000. So that probability is like roughly 42%. Okay, 10 diabetics exactly. That probability is about 12%. 13 diabetics, we can do that. More than 13 or more. That probability is about 20%. So what that means is that survey result, right, where those people got 13 diabetics, even in a population where the chance of somebody having diabetes is only 10%, 1 out of 5 surveys that you do, you're going to get a result with 13 or more diabetics. That's what that means, right? Roughly speaking. Even getting 20 diabetics, let's see what the chance of that is. So here we have the result only has 17 rows. So if I saw 20 diabetics, that'd be 17 out of 10,000. That is basically 0.1% chance of seeing that result. So if I saw 20 diabetics, there's very low chance that the population rate is only 1 out of 10. So if that had been the result, okay, there's probably something going on. But 13, not that likely anything is really different. Cool. So we can even make a histogram. So what's maybe the easiest way to do that? Let's do it like this. What? There we go. Okay, so you can make this histogram a lot of different ways. This is a kind of cute little bit of syntactic sugar. It's kind of like the pipe. This one comes from the Magritte library, but it basically says the thing on the right hand side of this, whatever that is, if you find a variable that you don't recognize, look for it as a column of the data frame that's on the left hand side. So I could have just written this like this instead, but I think this is kind of gross. I hate seeing the dollar sign. And then in other kinds of calls where you have a data frame, you're reusing a lot of different variables from a data frame. You end up saying like data frame $ variable 1, data frame $ variable 2. It gets gross. So I really like this little bit of syntactic sugar that says pull those columns out of this data frame. So it's like the pipe, but you have the dollar sign in there, just to kind of like remind you of like this kind of syntax. So that's a dollar sign. Anyways, use it if you want. Don't if you don't. If any code that you see that's confusing, you don't know what's going on, then of course, again, remember, just copy paste it into ChatGPT. Say, what is this doing? Why is it like that? What's the different way I could have done it? Explain it to me a different way. and that's usually a good way to work through this kind of stuff. But anyways, let's get to the result. So this is the histogram of how many diabetics were in our sample of 100 people from the New Zealand population when we reran that sampling 10,000 times. So what we see is that oftentimes you do get a sample with exactly 10 diabetics in it. About half the time you're going to get a sample with more than 10. About half the time you're going to get a sample with fewer than 10, again, roughly speaking, this is exactly the qualitative results that we had when we were answering those questions before, those conceptual questions. But now we can see it empirically by running a simulation, or we have a fake population data set and we can just sample from it. So that's why it's so nice to have these fake population data sets. You can really tangibly get these kinds of results instead of just relying on theory to understand what's. And of course, getting a result with 13 or more diabetics doesn't really say much, because there's a lot that happens a lot of the time, even though all of these samples are drawn from a population where it's only one out of 10 have diabetes. So hopefully that was useful to you. Remember, this is a kind of academic exercise. We never have the full population. We never have the full population of surveys. Even in this case, we just took 10,000 surveys and we said, hey, that's good enough to approximate the population of all possible surveys that we could have done, all possible samples of 100 people from this 5 million person population. We don't really even computationally have the power to generate that full population, so we approximate it. But in the real world, you never have this. You just have a single sample. You never have the whole population. But this is still a useful exercise precisely because we can contextualize the findings of a single survey or of a single study by thinking about, hey, what would have happened if I could have redone this, assuming something is the case, like assuming the rate really is 10%. Turns out that getting a sample with 13 diabetics is pretty likely.